homeworks on Blackboard and 3 tests on Blackboard. There'll be another homework given out tonight that we do next week. There'll be another homework given out next week that we do the week of the final. Right? I'll grade that homework prior to finals week and post that on Blackboard with all your homework grades so you'll know what you have on your total homework grade. I'll give you a copy of your total homework grade to potentially compare which one's your lowest grade to potentially drop for the class. So you make on a final exam. Do we have any questions on that?
Is the final exam gonna be like over everything, or are you just gonna have it like what's?
Final exam will be over the last couple of weeks.
Okay, got you.
But you will have to know how to use formulas given the information we've already I'm not going to go back and ask you to do a summation sign, right?
Mm-hmm.
The summation sign is going to appear in the later formulas. I'm not going to ask you to go back and recalculate means, either for populations or samples, right? But the means are going to show up in the formulas. So you're going to have to know how to use those formulas using the information from your class. You're going to have to know how to calculate probabilities, given what we've just been talking about, how to interpret probabilities. That's where I'm going to start with tonight. But yeah, all this information is going to be built into this last week or so, where information is going to start coming together. I'm not going to have you regurgitate earlier information because that information is already embedded in the current formulas.
Yeah, because we were out for snow.
Well, we missed 2 days.
I mean, that was a long time.
You gonna like based on your other classes, the last test easier than this one?
That's not how the classes typically work, but it generally happens that people do okay on the final compared to earlier tests. Final exam in the past has been comparable to grades in the first test in the past 4 classes like this. So I anticipate we're doing well enough on the final.
So, if we're like certain that the final is the one that we want to drop, but we still have to take it, correct?
Yes.
Okay.
I still want you to take it.
Okay.
If there's more leeway with it in this class than other classes, but yeah, you should still be here to take it. I'm sorry.
Even if we
I
just
apologize, I
circle a
have
couple of
standards.
things and we can just circle a couple of things and
Be on a merry way.
go.
Are you really comfortable with things in life doing it that way?
You only need a D to pass this class.
Well, if you want, I can give you that now. I mean, you're happy with the middle.
I'm really just tired. I'm burnt out.
Yeah, for real.
I won't lie.
2.5 weeks left to go.
I don't know if I'll be here the last week. I'm gonna be honest.
You can push through.
Could I take it early then, even if I don't know the information? I don't know what I'm gonna make, but I know it's gonna be like all you need is a D. But I'm not happy with the
It'll be
minimum.
easier than you anticipate.
Just so burnt
What
out.
do you mean by that? Is there an option to take the last exam after the last class?
Probably not. I tend not to do that. That creates scheduling problems.
Can you have an early test day?
All right, so we talk about probabilities basically associated with Z-scores, right? Broadly in class. We talked about single score compared against the sample mean, right? Sample standard deviation. We talked about, well,
I'm burnt out.
another Z-score. Single score compared against population data. Talk about sampling distribution of the mean, which is this group of scores, sample of size n against some population mean, which is known. Notice that for a Z-score, or let's put it this way, for the sampling distribution of the mean, you must know population mean, population standard deviation, sample size, and a sample mean, right? We talk about other ways of calculating probabilities, like using probability rules, all right? Addition rule, multiplication rule, those are not going to show up again specifically. Not specifically. We've also talked about calculating probabilities with regard to things like binomial distribution, right? If I had a binomial distribution, if I put in something like n, r, q, n minus r. That can also create a number which gives you a probability of an outcome, right? In every one of these cases, as well as the cases currently coming up, right, you're calculating based on known data, right? A priori assumptions, probability of specific results, right? Probabilities associated with normal distribution. In every case, you have a known set of population information, a known set of distributed information, okay? If the probability of the results you get back, if the probability is less than your alpha level, which usually is a 0.05, doesn't than half a meter, which is less than your alpha level, right? You are essentially going to reject your null hypothesis. That's what we did last class. Null hypothesis, 8-0. Alternative hypothesis, called H1. Okay? All of the probabilities you are working from to make the decision here derive from the knowledge a priori from your null hypothesis. You're assuming the population data, you're assuming the information from a normally distributed set of population numbers. Right? So you're starting with the null hypothesis. This is your default decision. Okay? Null hypothesis is your default position. If somebody asks you, hey, is this thing happening? Your answer without knowing anything is no, it's not, until you have evidence that it is. If you have evidence that it is, that means your probability is going to be so small, right, that you can't say it's not happening, right? Problems in the homework I pointed out a minute ago. If you have people coming to check out, the probability that person, the number of people with that particular number of orders is 0.00003, right? That is mathematically unusual. You can't say nothing is happening, okay? This is going to be an important point. I'm going to modify what I said a minute ago. You start with the null hypothesis, right? Must, by default, start with the null hypothesis. All of the data, all the formula assumes the null hypothesis is true, okay? All of your decisions then must revolve around the language dealing with the null hypothesis. You either reject the null hypothesis or you fail to reject the null hypothesis. Right? You have two possibilities for your decisions. You either reject the null hypothesis or you fail to reject the null hypothesis. This is going to be important because this is a little bit of the logic here. Saying you fail to reject the null hypothesis does not mean that you accept the alternative hypothesis, even though that seems intuitively obvious. Right? Let me give you a quick counting example. People use kind of, suppose you got a big jar of M&Ms, right? Take a pound bag of M&Ms, something like that, right? And I ask you, do you think the number of M&Ms in the bag is odd? Right? You say, no, it's not odd. Then I say, so you're saying it's even?
No.
Oh, exactly. Just if I say it's not odd, that is not equivalent to saying it is even. You either say it's not odd or it is odd. You either say it is, or basically it's not, or it's not odd. Right? Yeah. You can't ever accept the alternative hypothesis. You can never say anything about the alternative hypothesis, barring extreme statistical situations.
So like, why do we know about it?
Because it's an alternative to the null hypothesis, right?
This is
But
good
if
for
your
criminal
options
stuff.
are mutually exhaustive, like.
You don't know they're mutually exhaustive. That's the problem,
Okay.
right?
So that was just an
You
example.
know they're mutually exclusive. The assumption loosely is they're exhaustive, but you don't know that, right?
Okay.
There could be any number of things. This goes into methodology. That's why I started what I have methodology with a 210 class. In the area of science, when you run an experiment, right, you have some independent variable. How many levels does the independent variable have to have?
At least.
At least two, you're correct.
Oh yeah, you were correct.
I can see where she was going.
Yeah, me too. Oh, she's gonna say two.
And at least two variables, two levels of your independent variable, right? You want to know, are these two things different from each other, right? You can never say they're different from each other, right? You can say they're not equivalent to each other, right? If you reject the null hypothesis, you say something weird is happening, that means they're not the same groups. But if you fail to reject the null hypothesis, you can't really say they're the same because they might not be, right? You can only say they're, well, you can say they're not the same. You can't say they are different.
That's confused me. Just
So reject the whole or fail to reject the whole?
No. Yes.
No.
ho. No ho.
That's an easy way to remember for me. 'Cause
You either reject the null or you fail to reject null. Occasionally, you might hear retain the null.
Oh.
If you fail to reject,
then you
I think
keep
your
it.
textbook actually uses that.
Retain means to keep, huh?
Yes.
If you fail to reject, that basically means you're keeping it.
Yeah, so
Yeah.
you retain.
I don't like that, cause I don't want my man to retain the whole.
Those two things.
Well, no, I don't like that because will you ever use that on the test?
I will typically use reject or fail to reject.
Okay, thank goodness. Because if I just see the word fail, I'm gonna think.
Now, logically, these two things must be mutually exclusive and exhaustive, right? These two, because I'm only dealing with the null hypothesis.
Oh, yeah.
But the alternative is a separate curve entirely. Right? Now, let's point this out. When you're making a decision using inferential statistics, you must ultimately choose either this or this. Okay? You have to make one of these two choices. Can't understand anything about the alternative hypothesis. And this is the really nice thing about this area, right? It's really not a decision, right? You set this up as if the person looking at it goes, well, I could go this way or I could go that way. You are not making a decision here. The numbers will specifically fall into areas which force a decision. The numbers must produce one or the other of these answers. There is a decision point. If you're on one side of the decision point, you must claim the null hypothesis. If you're on the other side of the point, you must claim not the null hypothesis. Or, let me say this, you either reject the null hypothesis or you fail to reject the null hypothesis. That's entirely determined by the math, right? The math is then predicated on what's the probability of your outcome compared to this value you set ahead of time. You get some numbers your outcome. If the probability is less than your alpha level, right, you must decide to reject the null hypothesis,
Okay.
right?
So if the probability.
I'll write it on the board.
Girl, please.
If your probability is less than alpha, you must reject the null hypothesis. If the probability is greater than, or let's say equal to, for the reject. If it's greater than alpha, right, you must fail to reject the null hypothesis. You talk about decision theory here. There is no decision. The numbers tell you what to write down, right? The numbers tell you, you're either going to write this down or you're going to write that down, depending on whether your number is really small or whether your number is bigger than that, right? The probability comes back from, if the likelihood of a given result is, let's say, 20%, right? You must choose, fail to reject the null hypothesis, because 20% is bigger than 5%, right? If your probability comes back 3%, right, you must reject the null hypothesis.
So is that thing always 0.05?
For our purposes, mostly.
Oh, okay.
Occasionally it'll be a 0.01. I mentioned this last class. Occasionally it's a 0.01, right? Occasionally, even more rare, you may see it in the literature. We're not going to do anything other than 0.5 and 0.1. Right? But occasionally in the literature, you may see it as a 0.05. You may see it as a 0.001. Right? It should generally, right? Because if it's 0.5, that means there's a 1 in 20 chance, by random chance alone, that you're going to reject the null hypothesis. Right? Think about this for a second. We did this at the very end of the last class. If I say, what's the probability of rejecting the null hypothesis? Knowing nothing about any situation, what's the probability of simply rejecting the null hypothesis?
50-50.
No.
Just kidding. 25 out of
0.5.
Oh.
Oh.
Okay. Which means there's a 95% chance that you will fail to reject the null hypothesis.
Why is that?
Because 1 minus 0.05 is equal to 0.95.
But why is this 0.05? Like, why is that point?
Yeah.
It could be 0.06.
Well, but what I'm saying
Could
is,
be
why is that
0.07.
so small? Why is it more likely to reject? I mean,
Because you
why
want
is
to
it
make
more
sure you're
likely
making
to
a good
fail?
decision.
Okay.
Let me go back to the example you already used in the class, right? Suppose you're playing cards with somebody, and they're winning, and they're winning, and they're winning. And you think you're the same skill as them, but they're winning, and they're winning, and they're winning, right? And you think they've won so many, something unusual is happening here. The probability of them winning this much is way less than 1 in 20.
Okay, I see what
Right?
you're saying.
Question now is, do you pull a gun on them?
Yeah.
Absolutely.
That's
Literally.
Are you that sure yourself?
Like,
Absolutely.
Maybe they're just getting lucky,
Because why they cheating?
right? The probability that
But a
they're just
gun?
getting lucky is also 1 in 20.
Yeah.
Right? You don't know if they're just getting lucky or if they're really cheating on you. right? And 1 in 20 is a reasonably small number, but there, it happens. You play 20 card games, 1 in 20 times, you're gonna get that result.
That's right.
Or
Right.
they're just not really that.
You could set your alpha level to be 0.01, which would mean that 1 in 100 times you will reject the null
Okay.
hypothesis.
Are
Which
we
is a
going to
stricter
get that
criteria.
number in the question?
Yes, that number will give you
So this is 1 in 500. Never mind.
0.05 is 1 in 20. 0.05 out of 1.
Okay, okay.
0.01 is 1 in 100.
Okay. It's 5 out of 100 or 5.
0.05 is 5 out of 100, which is 1 in 20.
Yep.
So it's like 5%.
That's what I just
It's
said.
5%, 1%.
Girl,
You'll see some results that are 1 in 10,000. Right? They're incredibly rare. I'll give you another example.
Okay.
This is probably it's a good example. Years ago, there was a guy named James Randi. Right?
Who was he?
Huh?
Who was James Randi?
James Randi was
Is he
a
real?
oh yeah, he's a real person.
Okay.
He's dead now. But he died 8 years ago, 9 years ago, somewhere around. Not real, well, for years into the early 1920s, 1930s, he was essentially a stage magician. He was also an escape artist in his youth. As he got older, he stopped doing the escape stuff because it required more effort on his part physically. But he was an escape artist, right? Arguably like Houdini. Right? Decent, good, very well practiced entertainer. Started doing stage magic later on in his life. Started investigating psychics later in his life and debunking them. Right? Set up in the 1970s a thing called the James Randi Challenge. I come to the organization of James Randi Educational Foundation, but he set up this challenge. And he essentially said that anyone who could demonstrate under scientifically controlled conditions any psychic ability whatsoever, and you could name your psychic ability. If you thought you could do one thing that nobody ever heard of, you could write it out, you could claim that. Anybody who demonstrated under controlled experimental conditions got paid on the spot $1 million. Originally it was 10,000, but he got donations from a large anonymous benefactor and it bumped to $1 million by the early 80s. So it was $1 million prize, right? It was showing, right? Did not use an alpha level of 0.05, right? Because that would mean if 20 applicants came in, right? Even if they couldn't do anything at all, randomly 1 in 20 of them could take the money, right? Set up two rounds. One was a preliminary. The preliminary is you simply show the effect, right, to an alpha level like a 0.05. But then you had to show it again on the second test. You had to show it to an alpha level of 0.001, right? Because then the odds of you actually being successful, right, is 1 in 1,000, randomly. If I'm flipping coins, I say, hey, I'll tell you what, you flip this coin 1,000 times. If it comes up this many heads, I'll give you $1 million, right? You can calculate the number, the probability of the outcome of any number of heads based on the binomial distribution of what that outcome might be. We'll say 20. So I flip a coin 20 times to get closer to the table. It's back to textbook. Even 16, right? I mean, what the binomial distribution is, I can give you a real number on it. So I'm looking right here at binomial distribution. Suppose you're flipping a coin. You flip the coin 15 times. That's the bottom right here, the biggest number you got on the table. Right? And I say, if you flip that coin 15 heads out of 15, right? I'll give you $1 million. Right? You start going out in public, right? Somebody's going to come in, they're going to do that. Right? If 10,000 people try that, right, there'll be at least one who hits it randomly, not give away $1 million to a person who didn't do anything special. Right? So you want to make the odds very, very small. Okay? There are two types of errors here. Right? If you are setting your alpha level to be very, very small, right? Alpha level is equal to the probability of making a type 1 error. A type 1 error says something unusual is happening when in fact nothing is. There's a 1 in 20 chance that nothing really is happening interesting. Right? And if, because my decision mathematically falls in that low probability, I say I reject the null hypothesis. I have to say that the probability is that small. Right? I can easily be wrong. Maybe nothing is real. Maybe the person's not really cheating, they just got lucky that day playing cards. Maybe they happen to be the one person who flipped those coins and got it right. If I take, seriously, you can actually get this, you can demonstrate this. If you say, what's the probability of flipping 15 heads in 15 trials, right? 15R, 15N, 15R, 0.50, it's basically 0.5 to the 15th power, right? Which is really, really low odds. Right? I'm gonna start with 10,000 people. Everybody in the big audience, have everybody flip a coin, right? Everybody who flips tails, sit down, right? That'll get me down to 5,000 people, give or take. Or then flip the coin, right? So everybody gets tails, sit down. Now everybody's still standing, flip 2 heads, right? Have everybody still standing, flip it again. If you get tails, sit down. Now I've got 2,500 people, right? And every single flip, I have everybody gets tails, sit down, right? But given that large number of starting points, right, someone is going to flip a string of heads together, right? And they'll think they're special, even though it's just randomly in that big a crowd, right? Saying things like probability of an event is 1 in a million, right? It seems like it's never going to happen. But if you've got 1 million people starting with and trying it, it happens guaranteed, right? So it's a 1 in a million chance. You have to realize that happens 320 times every day to people in the United States, right? You want to try to minimize that error, all right? Second, this is what, let me do this is kind of a review from last class. This probability, your alpha level, is also equal to the probability of making a type 1 error. You don't know the real world. You only know the numbers and the decision you're making. So you might reject an hypothesis because something weird is happening and weird happen, or it may just randomly fall that way and you made a mistake. You made a mistake, it's a type 1 error. But you don't know that after the fact. If the probability is greater than alpha, right, there's a 95% chance that you make a mistake, right? The probability of essentially saying nothing is happening when in fact something weird is happening, that's beta. Well, sorry, that's one of my beta. That's your type 2 error. Well, I did type 2, I did Roman numerals last time.
What did you say last week about it not about beta won't know the value or something? Said something about
You never know the real world. You're playing cards with somebody, you're getting probabilities, getting results, getting statistics. You never know for sure if they're really cheating. You know, for example, if I were to play cards with you right now, right, knowing what you know about me from the last couple classes when I was dealing out cards, right?
that you're a cheater?
No, that I have the possibility of cheating, right? Question is, if I win a bunch, right, or the results come out in certain ways, did I actually cheat, or did the odds just happen to favor me? Right? You never know that. And a good gambler is never going to tell you, right?
Yeah, I'm a
Ne-
cheater.
Huh?
They're not gonna say I'm a cheater.
None of them are going to come in and say, I cheated you, right? They're going to make a guess at it, right? The math makes decisions independent of guessing. Let me give you a different example, right? Maybe a little bit closer to home. Suppose you give a multiple choice test to a bunch of students like yourselves, right? And I look at how many answers you get right, and I look at how many answers you get wrong, okay? If you've got a series of answers, right, let's take the multiple choice test, 15 questions on the first page, right? If you get 15 out of 15 of those questions right, if you were totally guessing, right, you didn't know anything at all, and you're totally guessing, right, that's 0.25 to the 15th power. The probability that you get all those answers correct just by guessing at them is astronomically low, right? But another thing that could happen is you studied, right? Maybe you knew the material. You got 15 out of 15 because you studied and knew the material, right? Or maybe, right, you got 15 out of 15 because you were cheating. You didn't know the material, but you had your notes. You had your phone next to you, so you're looking everything up, right? All I know from the instructor's perspective is you got 15 right out of 15. I don't know if you did it randomly. I don't know if you were guessing and got lucky. I don't know if you cheated, right? I don't know if you actually knew the material. All I know is you got 15 out of 15 right. Okay? I'm not going to accuse you of cheating, right? On the off chance that the probability of making type 1 error is there. Right? If I'm accusing you of cheating, I'm saying, hey, something unusual is happening, and I'm identifying what it is, but I don't know for sure what it is, because I don't know your lives that well. Right? Doesn't have to be a test, it can be law, right? Going to some legal system, right? Somebody's in front of a judge, they're being prosecuted, right? They're being accused of a crime, right? What's the default assumption in our country?
Innocent until proven guilty.
Supposed
They're
to be.
innocent in our country.
Well, that's what it's supposed to
That's what
be,
they say.
but in real life, like,
And you're sitting on the jury.
You gotta
Right.
prove you're innocent.
Prosecutors presenting evidence, defense is presenting evidence, right? You have to make a decision, right? Either you claim the person is guilty, right? That's equivalent to your alpha effect, yes, that's guilty, or they are not guilty. You never make the decision, they're innocent. They're either guilty or not guilty. That's the logical distinction.
Not guilty means innocent.
It's loosely interpreted that way, in the same sense that rejecting the null hypothesis loosely means you accept the alternative. But you can never accept they're innocent. All you can say is they're either guilty or not guilty.
Yeah, 'cause they could be mean in other ways.
Because they could be guilty in other ways besides, and they don't necessarily have to be innocent of the crime they committed, or not. Right? But the real issue here is, the deep issue here is, do you ever really know?
No.
You never really know, right? You're making a decision based on evidence, you're making a decision in this context based on probabilities.
Yeah, a lot of folks done got away with a lot of stuff in.
So here I'm gonna repeat. The default decision, the starting point, right? The assumption behind the equations for all these, you're assuming the null hypothesis is true and in place. If the null hypothesis is in place, you set up a series of probabilities from which you can make decisions. Alright? So let's do a couple of quick ones. Then we're gonna go into, I'm using the z-test we've already done.
We're about to do a problem.
Yeah, no problem. Suppose you're wandering around the building. Huh?
I do that often.
Why not? You've done what I'm about to describe, but let me know.
Oh, no.
You're wandering around the building, right? And you're going up and down the various floors, the various stairwells in the building, right?
All of
Because the different stairwells are positioned in different places in the building and so forth, right? Let's assume, I have not counted, I do not know, that the average number of steps between floors is 20, with a standard deviation of 2, right? And there might be 18 steps in one area, right? You might go across the hall, you might go down over here, it might be only 16 steps, right? It might be 9 and 9 on the next one, or 9 and then 10, right? Average number of steps is 20, standard deviation of 2. You wander around the building, right? You get in one of the weird little places in the little connecting between our primary RPC building here and up the hill, where they connect it to the next building up the hill. And you come across a stairwell, and I don't know if this is accurate, I'll just throw it out there, right? Assume these numbers are representative of the number of stairs in all the buildings in all the world, so that's population data, right? And assume that's normally distributed, right? You find a building that, let's say, has 9 stairwells, right, with an average number of steps at 23, right? So you got average number of steps is 23, right, from 9 stairwells. What's the probability of finding a building that has 9 stairwells, averaging 23 steps per stairwell, when the population averages are set up as 20 and standard deviation of 2? Yeah, quick question. What formula are you going to use?
The one where you divide that.
You have 4 numbers here. There's your 4 numbers there. That equation. So I end up with 3 over 2 over 3. Which is 3 divided by 0.67. Right? It's going to give you about a 4.3 or so. I'm guessing you're going to be pretty close to that. Mhm.
It's gonna be 4.48.
4.4, that's a little higher. 4.48. Okay. So the question is the building with those 9 stairwells unusual?
No.
What's the null hypothesis?
Is that 4.38 over there?
Wait.
It's a 4.48, if you just did the math correctly.
Is it unusual before we answer the next question?
Yes, it is.
Hang on.
Okay.
Cause it would
You
be
would
all
change
The
these
first
four
step,
were-
there's your numbers, there's your math, put that aside for a second.
Okay.
The average is 20.
What's the null hypothesis?
Nothing unusual is going on.
Okay.
Do we write that out?
You can either say nothing unusual, or you can say another way to say this is, a lot of people say this, your sample mean is equal to your population mean.
So we can write nothing unusual though.
Or you can say there's no difference between your stairwells. There's no
Okay.
difference between this stairwell and the population stairwells,
Okay.
right? Typically you want to put in the language of whatever your problem is set up as.
Oh.
But yeah, nothing unusual means the stairwells are all equal to each other. Another way to say it is, the stairwells that you drew as your sample are actually drawn from the population distribution. Right? If I were to draw my z distribution, means 20, right? Somewhere up here I've got 23. That's part of that distribution, because distribution is infinite in both directions. Right? The z-score sets up as a 4.48. Z-score is 0 in the middle. Right? If I ask what's the probability of drawing this z-score, that number of stairs, right? Given these population parameters, right? The population there, without looking it up specifically, is going to be less than 0.0003. That's as high as we got on the table before. The z-score of 4. Right?
Which is less than 0.05, so we reject the null hypothesis.
Correct. Haven't quite got there yet. We'll make sure that you catch up. Yes. Right. If the null hypothesis is that nothing unusual is happening, or the sample is in fact drawn from the population mean, the alternative hypothesis is that the sample mean is not equal to the population mean. Right? Something weird is happening. The two means, sample, population, are different from each other. Right? These are my two choices, right? Which one do I decide is correct, given those numbers? If alpha is equal to 0.05, the calculated outcome is 0.00003, less than that, right? Just calculate there. Which of these two things do I decide? The second one, but I can't accept the alternative hypothesis, so what I say is instead I reject the null. Right? The probability of getting this result is so small, I'm going to reject the null hypothesis. Does that make sense? I'm going to say, hey, that building with those 9 stairwells, that's an unusual building. That's so far out of the realm, because I expect a building with 20 stairs in it. This one's got 23 on average. Right? Does that make sense? All right, so now we're going to go into the new stuff for today. That's the hypothesis. I think that's going to keep showing up over and over again, similar types of stuff. There's going to be variations of it, especially when we start talking things like one-tailed and two-tailed tests. But I'll leave that up for now. Using the z-score calculation, right? You must, as part of the z-score calculation for the sampling distribution of the mean, have a known population mean, right? And you must have a known population standard deviation. And you must have a sample of a given size, right? You have to have those numbers to feed an equation. What happens if you don't have a known population standard deviation? So in other words, if you don't have sigma, but instead, well, saying sample population is a long language, using the sample data. If I have a sample, right, I can calculate a standard deviation of the sample, right? Going back earlier in the class, we're not going to do this again, but from earlier in the class, here's my standard deviation. Sample standard deviation looks like a similar formula, except denominator has n-1. Those two formulas are close enough together that I can use my sample standard deviation to approximate my population standard deviation. Right? But if I'm approximating the standard deviation from the sample, I can't use the z-scores. Right? I can only use the z-scores if I know the population parameters, mean and standard deviation. Since I don't know the standard deviation for the sample, I don't know the population standard deviation, I'm relying on the sample standard deviation, I can't use the z-score. Instead, what I'm going to do is I'm going to use a t-score. I set up our first t formula for t-tests. That's my first t-test formula. point out, watch what's over there. Sample mean, population mean, standard deviation, square root of n. That formula is identical to this formula, except instead of sigma, I'm using s. But changing the sigma to an s, I have to change the z to a t. Right? I can't use the z distribution anymore, but I can use a t distribution. Right? This also then transfers, same formula, I'm going to expand it given what I just wrote on there as a standard deviation. Notice I got a square root of n here. If I put the square root of n under this, right, the denominators collapse into each other mathematically. When I go through the algebra, you get this. So this n comes from this n, square root of sample size. This n, minus 1, comes from the standard deviation, and minus 1 here. Same n in either case, same number numerically. But this becomes a calculational formula for a t-test.
So we'll have to sit there and figure out.
Some of the questions we're going to start with, I'm going to give you the basic information. There's going to be 4 pieces of information that we're going to plug in. I'm going to give you sample size, sample standard deviation, population mean, sample average. I think I said 4 over here. These 4 numbers. You just be able to plug them in. For some of the things we're going to do, on homework tonight, I'm going to give you, here's a sample set of scores, and you'll have to calculate the standard deviation, then plug it in either here, or you can calculate it as part of the bigger equation as you're going. Right? So you can either calculate the standard deviation by itself and plug it in here, or you can calculate the standard deviation as part of the bigger equation for the second part. These 2 equations are identical to each other. All I've done is substitute in the bigger formula for s in the denominator. Common sense? We'll do some examples of that in a minute. The t distribution, I'll draw it a little more specifically than I did a minute ago. Looks vaguely like this. I say t distribution looks vaguely like this. There's actually a diagram in your textbook I'm going to try to replicate here. Right? It's very much similar to the z distribution, right? Except in general, the tails out here, right, are bigger. In other words, if I were to draw a z distribution, we draw another distribution on the top of this one. I'll try to draw it a little more accurately. If this is my z, that's my t.
Are we gonna have to have double ones, like make double graphs
No.
like that? Okay.
Like that one, no.
Alright,
No, you're gonna have a single graph from which you are making decisions based on probabilities like you've already done.
okay. That's gonna be on the exam too, right?
The relationship between the t distribution and the z distribution may show up as part of the assumptions questions on the test.
Okay,
Yes.
will we have to draw?
You will not have to draw specifically t distributions, no.
Okay,
You will have to make decisions, and drawing it might help, but I'm not gonna require you to draw the t
Okay.
distribution outcomes. This hopefully is gonna come back together a little more once I actually start getting to the point of making decisions.
okay.
So here's the idea. Z distribution has that curve like we already talked about. For both the t and the z distribution, center is equal to 0. Right? For both the z and the t distribution, half is above, half is below. They're both symmetrical around the mean. Okay? For both the t and the z distribution, right, you can calculate probabilities associated with any value of z, just like we've done, or you can calculate probabilities associated with the t value. Right? The weird quirk here is the exact presentation of a t distribution depends on your sample size. So the t here is relative to your n, right? As n gets larger and larger and larger, the t becomes a z distribution. So we'll draw it this way. So here's my z, right? If I were to draw another distribution between these, it's like a little dash distribution, right? So I'm gonna draw it this way. Here's my z, right? Let's say here's my t with, let's say a high n. Here's my t with a low n, right? As my t with a lower n starts showing up, the tails get bigger and bigger, and the middle drops down. Alright? as my n gets higher and higher and higher, the t distribution becomes a z distribution. In the same way that the binomial distribution, if you're dealing with symmetric binomial distribution, becomes normally distributed when you have a number of outcomes, number of trials greater than 30. Once you get past about an n equal to 20 or so, n equal to 30, right? Some people say 20, some people 30. Once we get to about, you'll see in a second, I'll show you the numbers. Once you pass about n of 30 or so, the t distribution pretty much narrows down to the z distribution, right, within a couple hundredths of a value. Okay?
What's the dash?
It's the value, essentially one of the t distributions with an n that is essentially higher than the full z distribution, or the full t above it. If I were to keep drawing t distribution, what if I keep making the n smaller? So I have something like t with n equal to 1, I might have something that looks like this. Right? Or that's like a t equal to 1, n equals 1. N's never going to equal 1. But conceptually, that's the way the graph tends to run. Point out something else here. May or may not have noticed it. I tried to draw it reasonably well, right? The point where these curves cross, this point right here, this point right there, those are the inflection points. Right, that's one standard deviation above the mean, or below the mean. All right, that's the inflection points. That's where the nature of the curve changes. Instead of being high in the middle and fat on the ends, it becomes fatter in the middle and shorter on the ends. All right, but that changing over point occurs at the flip of the curve, for the inflection point. So now here's the idea. If you've got some value out here, right? Some value out here at this point, right? Anything outside that area, right, is going to occur with a low probability. But that little point can shift left to right. So if it shifts inside, that area probability gets bigger and bigger and bigger. If it shifts further and further to the right, probability of the area gets smaller and smaller and smaller, right? If the probability of the results of your test come out in this area, you're going to reject the null hypothesis. The size of that area is determined by your alpha level. So the size of the area is typically going to be 0.05. That makes sense? Let's do another example.
With this, with the T?
Yep, with the T. I'll let 2 minutes ago. Actually, that might work. Let's do that. Going around the building again. I don't know if you notice, in Western got a lot of propaganda posters up like that. And we have them over there. Happy students. Right? They're not in stats classes. But,
You hate seeing our pictures, you said you removed them.
huh?
Remember the last class and there was one behind your head?
I didn't like the way it looked behind me. I didn't say I hated the picture. I didn't like the aesthetics of that particular picture behind me. And so I found one that I liked a little better and framed myself in the Zoom session. Huh?
All my cookies melted together. So,
Oh my gosh.
Are those cookies?
They will taste the same.
yeah. Here, you want them?
You know, when they melt together like that, they become poison.
Oh,
What?
Well, I don't know how to.
Apple
Wow.
I
wow.
believe it.
No,
Yeah, no,
they
they
don't.
No, they
Cameron,
don't.
don't put it on that nasty table. Now
You
you
know, if
may
it
not.
touches the table, it becomes poison.
Exactly. Now that's true.
I'm in a minute.
Kids nasty.
All right, so you're going around the various rooms of the building, right? This room has 2 pictures in it. I think the one across the hall has 4, maybe 5, right? Let's say the average number. Let's look at this one. Let's do this one. So give me average. We'll assume the population average for number of posters per room is 4. Right? That's the number of posters on average I expect. I don't know the population standard deviation. So I look in this room. This room's got 2. Let's see, let's do it this way. Let's put an X here. This room's got 2. The room across the hall has 4. Room down there has 5. A room has 3. Another room has 2. Right? Maybe one room has 1. Right? Oh, let's say another room has 5. Okay? So I go to a specific number of classrooms in this building. I sample this building. Okay? I get this number of propaganda posters in the rooms. Right? I ask the question, is there anything unusual about this number of propaganda posters in the WQ classrooms? Right? More specifically, I'm going to ask, based on these numbers in particular, is the number of my sample, is the number of pictures in my sample, let's say higher than the number in the population. I want to say specifically, let me write that little offset from that. We'll say is X bar higher than equal to the mean. Is X bar higher than the mean?
Yes.
Huh?
Yes. I think. If not.
Mathematically, you can know for sure.
I'm trying to do
Mathematically,
it in my
there's a
head, but I
guaranteed
don't-
solution.
I don't think I did it right.
So here's my sample, right? There's my population mean, right? How would I go about answering this question?
Add them all together and divide by
Seven.
7.
You get
Well,
3.14.
that's just gonna give me,
That's just gonna give you the mean.
let's get my sample mean. Let's do it this way.
Which your X bar.
Summation of x, right? It's gonna be 6, 11, 16, 17.
3.14.
How'd you make it 5?
When you divide it by 7.
Huh?
When you divide it by 7, you get 3.14.
Did you mean to make it 5?
No.
No.
But pi is actually close to 1/7. I don't know if you know that or not.
No.
7 multiple. It's actually one of the ways the original calculators, they started varying fractions around the 1/7, 1/6, 1/7, 1/8. Then they got more and more precise, like 2/14 versus 1/14, 3/14. Until eventually they had the mathematical calculations for it. But question is 3.14 greater than or equal to 4 is the mean. 3.4 greater than 4?
Nope.
No. All right. Let me change. Let's make another number here. Make one number different. Let's take that 1 and make it a 5. Right,
So
that now
wait, does that
becomes
mean?
26. Actually, let's go ahead and make another one by 2. So make another one here 5. And make a nice round number. So it's gonna be 28. Right? I think it's 28. No, it's gonna be 30. Yeah, it's 28. So their X bar was 4. Right? Yeah, so everybody's 4. In that case, is 4 greater than or equal to 4?
Mm-hmm. But it's equal to.
All right. If in fact you had the 3.14 or the 4, right, you would essentially fail to reject the null hypothesis because it's not greater than, right? If I did, let's say I got, let's do this way. There's a 12, right, which makes this value now a 38, which makes this value a 5.42.
4.2, 4.3,
Yeah.
rounded, rounded 4.3.
Oh, it's around 42. So 5.42 is greater than 4. Question is it statistically greater than 4?
No,
Oh.
because it's just a little. You always say when.
Well, you don't know how much it is mathematically. Make this point. Mathematically, there are 3 things that are going to be changing simultaneously here. You're going to keep track of. Oh, we're going to do it right here in a second. There are going to be 3 numbers that are changing simultaneously. All 3 of these numbers show up in the equation itself. Right? Notice in the numerator, you got the difference between the means. Right? That's one number here. How far apart are the means from each other? That's basically this. Right? 5.424. How far apart are they? Second number is S, standard deviation for the sample. We have not calculated that yet. Third number is N. In this example, N is equal to 4. Sorry, 4. 7. Make sure I say the right number. N is equal to 7. Right, mean was 4. Right? If I've got 2 curves, we'll draw 2 curves here. There's my population. There's my sample. Okay? The question is this sample drawn from this population? That's the big question here. Is it drawn from the population or not? If it is drawn from the population, you're going to fail to reject the null hypothesis. If it's not from the population, you're going to reject the null hypothesis.
What?
Let me redraw this slightly. If I had 2 curves that look like this, there's X bar, there's mean. Are those 2 curves the same?
Yeah. Yeah, look like it.
There's no overlap between them. Those are different sets of numbers, right? They'd be like saying, here's a bunch of numbers, 1, 2, 3, 4, 5, and here's a set of numbers, 10, 11, 12, 15, 20. right? There's no overlap between those. Those are different curves. Did this set of numbers come from that set of numbers? No. Did this set of numbers come from that set of numbers?
Maybe.
Maybe. Right? Here they didn't. Conversely, I'll draw another one here. Try to make the point. Are those two curves the same set of data or not?
Maybe
Which one's more likely to be the same, this one or this one?
that one.
That one.
This one's more likely to be the same, right? Be kind of like, let's do it.
They're
like-
closer.
I don't have, when I have the little chips, right? If I got the numbers, 1, 2, 3, 4, 5 on poker chips, and I put them in a bag and start pulling out numbers, putting it back, pulling out numbers, putting it back, right? And I say, what's the probability of drawing a number, right? Let's say with a sample of numbers with an average of 2.5, right? That's what you expect out of that bag, right? If I draw a sample aside where the sample average is something like 12, it didn't come from that bag, right? I must have numbers that have chips higher than 5 if I'm getting an average of 12 from it, right? That's like the one at the bottom here, right? If the values here go from say 1 to 5, and I got values coming in with an average of 15 or 20, that couldn't have come from the 1 to 5 bag. It's got to be a different bag entirely, right? On the other hand, if I'm drawing numbers out and the population mean is expected to be 2.5, and I get values of 2.6, yeah, that probably came from that bag, right? The separation in the means is mathematically determined by the numerator. Okay? The S is how much overlap there is in the curve. So here's a little overlap there, there's the overlap there. Here the overlap is everything in here. Right? The S is how wide are the curves around their averages. As the standard deviation gets smaller, right? So top. If this number in the numerator gets bigger, what happens to T?
It gets smaller.
We did this a couple weeks ago.
Gets
Bigger,
bigger.
smaller. One
If
of them gets
numerator here gets bigger, what happens to T?
Bigger.
It gets bigger, right? As the separation spreads out, T gets bigger,
Okay, yeah.
right?
Mm-hmm.
As the separation spreads out. As S gets bigger, what happens to T?
Gets smaller.
T will get smaller, okay? As S gets smaller, what happens to T?
Bigger.
It gets bigger, right? And, loosely speaking, as your N goes up, as N gets bigger, T will get bigger mathematically. In the real world, as N gets higher, T is more likely to solidify on a particular point and become more accurate,
Okay.
right? But effectively, as the separation of means gets higher, T gets higher. As S gets smaller, T gets higher. As the number of scores in your sample goes up, T gets bigger, right? I did a little fraction number a couple weeks ago where I had the A equals B over C and added D into it, and like this fraction. This is building this fraction. In order to reject the null hypothesis, you want your T value to be as large as possible. Because that means if T is getting bigger, if this is a T distribution, as T is getting larger and larger and larger, you're getting a probability smaller and smaller and smaller. Yes?
Yeah.
Let's take a break at this point. It's a little bit of a break.
This isn't the way we.
It'll be easier in a minute. Once I actually start doing the math, this will all just
Whatever.
trust
You
me.
say that every time.
Trust me.
Then I have to go and listen to Khan Academy and pay $300 for 4 hours and
I would not recommend it at all, but you know.
$300 for 4 hours?
something like that.
Yeah, good lord. Yeah, that's
And not
I think
literally,
there are
not
much more
literally.
efficient
Oh,
ways to
okay.
do things.
Not literally,
Woo!
but it's still,
I was like, girl,
it's still too much.
you are getting scammed.
I am.
Can I talk to you?
Sure. Here, there.
So I fixed the problem with this.